Welcome back. Although I don't like to speak too much about common space weather activity, and I'm concentrating mostly on more unusual data, today I'll speak about the latest impacts of two CMEs. On the ACE solar wind readings, we can see clearly two separate waves which were emitted by two different events. First wave came from an M4.6 flare. Second one, much bigger, was emitted during the X1.6 flare. According to NOAA, during the second impact, KP index reached 7 points, what means that we've had a G3 geomagnetic storm. Here we can see how both impacts affected the magnetometer readings in Norway. In the upper right corner you have the scale, which allows us to learn the strength of disturbances. But let's concentrate on the first one. If you saw my previous movie, you should already notice something odd. On the magnetometers placed closer to magnetic pole, there is no sign of any geomagnetic disturbances. It seems as well that in some stations, first impact affected our planet stronger than the second one. Besides, it seems that the impact took place around the time when this region is experiencing the daily geomagnetic jolts, which are not connected with any solar activities. And this is the best moment to look at the main factor which is responsible for the occurrence of geomagnetic storms: IMF orientation. Interplanetary magnetic field is much more important for our planet than the parameters of solar wind plasma, and the main value is visible on the second graph from top, BZ magnetic component. According to current knowledge about space weather interactions, a geomagnetic storm can take place only when the BZ is negative, what means that IMF is directed southward. During the first impact, BZ became negative couple times and reached -13 nanoteslas just before midnight on 11th of September. But before and after this shift, IMF was directed southward couple times. Most important is the fact that during the geomagnetic jolt in Norway, BZ magnitude was smaller than before, when no disturbances were recorded on ground magnetometers. If we will look even closer at the ACE readings, we will notice that BZ turned positive right at the time of geomagnetic jolt. To make it even more funny, the disturbance wasn't recorded in different regions of Earth, and it is known that CME impacts affect the magnetometers over entire planet, just as did the second impact. So what's my final conclusion? First disturbance was not caused by the CME, only by the low energy field influence, which was enhanced by the increased space weather activity. And it was enhanced greatly. In Lerwick, the jolt reached almost 700 nanoteslas. In Kiruna, jolt caused much stronger disturbances than the second CME impact. This is the auroral power measured by POES satellites. In the difference to Ovation Prime, it shows the actual, not calculated, energy influx. Around first UTC, the auroral power jumped suddenly from 7.5 to 111 gigawatts, only to drop couple minutes later to 46 gigawatts. Instead of a long duration storm, people on southern pole saw probably a rapid burst of colors, which were gone soon after. To finish with the first impact nicely, let's look at the magnetosphere, which experienced another hit of density spike, which caused a flip of IMF orientation. BZ turned positive, right at the time of auroral outburst. It seems that against the knowledge about geomagnetic activities, this shift caused a reconnection at the day side of magnetosphere. closed red field line, which formed the plasma sphere, was ripped apart and turned into two black open polar cap field lines. Time to look at the second extremely fast CME, which hit us just after 15 UTC on the same day. Velocity jumped rapidly from 400 to more than 600 km per second. Temperature and density grew as well. In the difference to previous event, a strong geomagnetic disturbance was recorded on the entire planet. And the strength was bigger close to magnetic poles. Clear sign that we are dealing with solar particles. However, instead of a drop, the geomagnetic field experienced a clear increase of magnitude. Auroral power grew immediately to more than 100 gigawatts. And this is the time to watch the interesting part of this event. Those are the ACE magnetic field readings, recorded during the second CME impact. But to understand the interesting part, you need to know about one of the laws of space weather. Strongest geomagnetic storms supposed to take place only when BZ component, yellow one, is negative. However, the geomagnetic field can be seriously disturbed when velocity of solar wind is very high. This time it reached 650 km per second. But there is a problem. Couple hours before the auroral power hit 170 gigawatts, the highest value since I started to watch the space weather, BZ component shifted southward and reached minus 17 nanoteslas. According to space weather models, it should trigger the auroras and boost up KP index. And this is exactly what we can see on the modeled Ovation Prime monitor. Highest value was generated at the time when IMF turned rapidly northward and soon after the auroras faded, as the BZ remained positive for next couple hours. Problem is that this monitor has nothing to do with actual values recorded by POES satellites. Sadly, I can't get the readings from the time when southward BZ reached the strongest magnitude, so I can't tell you what was the auroral power at this time. However, in the morning of 13th of September, when POES recorded the strongest burst of auroral activity, Ovation Prime was showing that geomagnetic field became almost perfectly calm. And even if the lack of data doesn't allow me to tell that strong negative BZ didn't cause any auroras, ground magnetometers show clearly that geomagnetic activity became weaker after the IMF turned south, around 20 past 20 UTC, while the disturbances grew again after the direction turned north 2 hours later, completely opposite to all the space weather models. Ladies and gentlemen, it seems that we need to change the books again. Another aspect which is clearly opposite the models is the charging environment. Magnetosphere is supposed to gain strength, while BZ is positive and become weaker when it turns south. Not any longer. Now our shields are being pumped up with energetic particles during south orientation of IMF and lose the power during storms, when IMF is turned north. With this statement, I've turned the knowledge about space weather interactions upside down. My conclusion is rather disturbing, as am I capable to figure out just one explanation of this anomaly: reverse direction of current flow in the geomagnetic field. Or to say it more simple, flipped magnetic orientation of the planet. Let's hope that it was only a very unusual event, because if it is a constant change, we will be in troubles. But let's look at the magnetosphere in the moment when Kp index reached 7 and G3 storm began. But look closely what happened at this time. It seems that besides the BZ turning north, there was as well a clear increase of velocity, what happened couple hours after the initial impact. But it's not even a half. Bx and By made a 180-degree flip as well. And soon after, the velocity grew once more, what was connected with decreased solar wind density. It looks like a third event, which is quite similar to coronal host stream with the frontal density wave. Check out the response of magnetopause position. This is the impact of a boundary between the initial CME wave and the mysterious wave which triggered the strongest disturbances. But the most funny part took place couple minutes later. Look what happened with the bow shock. It is clearly pushed away from Earth and against the incoming solar wind. Incoming waves of increased density push the bow shock back towards the planet, but only for a while, as the opposing backside force is not giving up. It manages even to push it out from the field of view. Each impact of solar wind is causing an opposing reaction. Now look at the middle of magnetopause, where we can see a giant breach in our shield. Soon after, another impact of solar particles takes place and hit the damaged magnetopause. During this event, POES recorded another enormous burst of auroras. Energy influx reached 124 gigawatts. Of course, BZ was at this time positive. Do you have enough? No? Good. There is more. Since the beginning of 12th of September, we were experiencing backside gusts of neutral particles. What shouldn't happen during impacts of super-fast CMEs? Gusts stopped when the storm reached G3 level. Time for a break. Now something more spectacular. Atmosphere shaped by electromagnetic forces, dipolar field lines and a huge vortex. If you will look closer, you'll notice three smaller whirlpools which formed around the central low-pressure system. Let's move back to ISWA, where I'll try to show you quickly how the CME impacts affected the ionosphere. Let's start from the HMF2 monitor. Look how the first weaker impact affected the height of electron cloud. It is clear that during this event ionosphere was compressed by the incoming wave and almost entire electron cloud was pushed closer to the surface. Second interplanetary shock, caused mainly by a great increase of velocity, didn't affect the ionosphere too much. But when the BZ component turned southward, the height of equatorial magnetic connection grew to more than 1000 kilometers. But electrons moved even higher when the Kp index reached 7 points. Another effect of the geomagnetic storm is visible on the neutral gas temperature monitor. During the strongest geomagnetic disturbances, neutral particles were heated up to more than 1700 kelvins, around 200 more than ionospheric plasma. I've noticed some time ago that during CME impacts, one of the most affected particle is the atomic oxygen, single O. latest storm is not different, but it seems that the first impact from the midnight of 12th of September affected it much stronger than the G3 storm, which started almost a day later. Before I will move further to other aspects of space weather activity, I need to show you the polar cap potential monitor. It seems that CME is currently changing the code, and instead of kilovolts, it is switching from the joule heating data to values which I simply can't read, as I am too stupid. H can mean hydrogen, but I'm not sure about it, not to mention the sigma and omega. However, something is bothering me on those images. Look at the angle between blue and red fields. It looks that charged particles arrive at Earth from a side and not directly from the Sun. And what the hell is that white field over the dusk part of Southern Hemisphere? It seems as well that the end of the geomagnetic storm didn't stop the energy influx from the side of planet. To make it more funny, the red field started to shift towards Northern Hemisphere. Only to move back south couple hours later. I have no idea what it can mean, but the red area seems to wobble over the equator. Maybe I'm completely wrong, but I think that it can be connected with the cosmic rays activity, which was seriously decreased by the geomagnetic storm. But just when the KP index dropped, we were hit by a strong cannonade, what caused couple serious jumps of cosmic ray density. Since the last time when I used those directions in my 3D model, the angle changed a bit, exactly as I expected. I think as well that the cosmic rays didn't still finish with us. A lot of monitors is missing the latest readings, and those which still work show a clear increase. This is probably the source of this huge low energy particles burst, which was connected with couple density spikes recorded by ACE at the same time. and because low energy is connected with low frequencies, this disturbance on Schumann resonance was the effect. The fact that it was recorded on Earth faster than by ACE shows clearly that it wasn't caused by any kind of solar activity. For the end, look at impacts of these spikes on our magnetosphere. Okay, enough of this fear porn. Class dismissed. Be safe. Peace.